Welcome Physics 20. So I'm going to go over this other practice exam that we have here. I gave this out on the Friday or the Thursday, depending on which day. If you got it on Thursday, you don't have the full one, so you may want to check out the PDF. I added some questions on here, which might be useful. And let's get going. So I'll post obviously the PDF later on. So let's do these questions that are over here, down there in that spot over there. Yeah, my hair's just getting in the way here. Whew. Been a long week. Okay, so a window washer is moving his squeegee back and forth over a stubborn piece of dirt on a window. He moves his squeegee up and down a distance of 1.2 meters 5 times. What's the total distance traveled? All right. Well, what's the distance traveled? So we've got distance and displacement, right? So it goes 1.5 up, down, up, or something. Let's assume that's the 5 that we did. Because it's 5 times, up and down a distance of 5. Yeah, okay, so maybe it's up and down 5 times, like up, down, 5 times, right? So I'm just going to times that first one by 5 because I don't really care too much about the distance. That's a pretty easy one because we talked about distance in this first one. Hope it's going to work. Yeah, good. So let's talk about distance. Direction doesn't really matter. I'm just going to go 5 times the 1.20, and we're going to get our 6.00 meters. That's the distance. But now if it goes back up and down, back up and down, back up and down. So if I start down here, let's say right about here, right, and then I go up, down, up, down, up, down, up, down, up, down, up, down, and I end up there. If I look at the beginning to the end, there's been 0 displacement that's happened, right? So if I've gone from here, this is my initial position, then up, down, and up, down, and up, down, and up, down, and then up, down, and this is my final displacement, you can see that there's, if I go df minus di, final minus initial, look at my displacement, I'm going to get 0. All right? This one's a good one. It's just going to talk about average velocity here, so, or average speed. This is vertical velocity, but there's no way to put direction in this question. To do the average speed or average velocity, you just have to take the total displacement and divide it by the total time. All right, so this, I know there's acceleration in here, but they're just asking for this average velocity. So we're just going to do the simple calculation. 807 divided by 14. And we're going to get an average velocity of 57. 57. No, it's a 2 sig digs. So I started writing this down already, so I'll write down some decimals here. But 2 sig digs is 58. It's got to round up. 3 blocks are tied together. Each have a mass of 2. They are pulled to the right on a frictionless surface, assuming even tension on each block. What is the acceleration that block of B accelerates at? Okay. So I don't see why you wouldn't assume, or even if I didn't assume it's even tension, it doesn't really matter. So frictionless, right? So if I apply a force only on this first block, and there's some ropes attached between these, of 30 newtons, the thing is, we got all these action-reaction forces, right? So this block, listen, this is block, what am I saying? Yeah, okay, let's just say this is block C here. C is going to pull on to block B, and then B is going to pull back on block B, or C. And then what's going to happen again is A is going to be pulled by block B, and A is then going to pull back, right? So we got these action-reaction forces. So if I were to look at, let's say, calculate the acceleration of B, and look at B, the problem is I have these 2 unknown forces. I don't know what they are, these 2 tension forces. But if I look at the whole picture, I can see that these forces are going to cancel each other out. Right? So the only F net I have for this whole thing is 30 newtons. I got all those gravities too, right? They're going to cancel each other out. Got gravity, normal force, gravity, normal force, gravity, normal force. Okay. Got to find the acceleration though. So that's going to be F net divided by my mass. So I got 30 newtons divided by my total mass because I used the block. Sorry. I put the circle around everything. If I put the circle around everything, I got to include all those masses as well because the only way to get these other forces to cancel out is I had to include them. So we have each with a mass of 6, and there's 3 of them, so 6 kilograms. Sorry. So it looks like I'm going to get 5 meters per second squared there. And the mass, this is 2 plus 2 plus 2, right? That's 6 kilograms. I'm going to write that down for later. Okay, so 3 forces are acting upon the same object. Right? A, B, and then we're looking for the force C. That's the magnitude of force C if the object is stationary. Okay. So, best to do is to draw a free body diagram. So here's my object. I've got a force that's going 270. So that's straight down. It's 270, 75 newtons. Then I got a force at 0 degrees, straight to the side, 15 newtons. And assuming that there's going to be another force somewhere right about here, right about there, that's going to try to balance out these other 2 forces. And what could they be? I obviously got this really garbage answer. It's probably because I forgot to do the square root or something. But to do this, we got to think about x's and y's, right? So what do we have? So this first one here, it's all x. So I'm going to say north and east are positive answers here. Right. Or there's no northeast on this one. So let's put my sign convention a little bit different here. There you go. So those 2 directions are positive. So I got positive 50 here, and because it's directly east, I'm going to say it's 0. And this other one I got 0, and then I got negative 75 newtons because it's going downwards. So I got negative. So if I add these 2 forces together and kind of get a net, like a subnet or something, but not the full net, of 50 newtons and negative 75, because I want this to be stationary, I need my F net to be 0. That means all the x's and all the y's have to add to 0. So therefore, there has to be another force here that's negative 50 newtons and positive 75 newtons. So there has to be another force that's going negative that direction, 50 newtons, and upwards 75 newtons. So we have this overall force here that we're trying to find. That's going to balance those other 2 out because you want to make sure everything adds up to 0. So we got this other force that of opposite signs to make sure everything adds up. All right, so 1575. We take the square root of that answer. And go to. There you go. I get 90.1. Okay. So to find that magnitude, I didn't really show it. I'm going to use Pythagorean theorem, right? X squared plus y squared is equal to r squared. So we got 90.1 newtons. All right, so we're going to use the following information to answer the next 3 questions. I'm assuming that's true. Okay, sometimes I say 3 questions, but then I might remove a question by accident. The first question is saying, for the first 7 seconds of motion, the motorcycle can be best described as doing what? So the first 7 seconds, that's up to here. So the first 7 seconds, let me just highlight that. Nice flat line. So the acceleration here, because if acceleration is equal to change in velocity over time, this velocity is nice and continuous. It's 0, right? So the velocity is just a constant velocity of 10 meters per second. So kind of looks like this. It's positive. Yeah. I'm going to assume that that part is positive, so we're going to say forward. So 10 meters per second forward. Okay, during the 7th second, what is the motorcycle doing here? Well, the motorcycle is kind of decelerating down to 0 and then speeding up in the other direction. But it's a nice continuous acceleration, right? It doesn't have like a stopping point where they stop and they have to change direction. So just like we did before, I can find out what the acceleration is here. Okay? I could do the change in my velocity divided by my change in time. There's only 1 second. So I put 1 second here. My change in velocity, if I go final, -10, minus my initial, +10, kind of looks like my acceleration is -20 meters per second. Put my head the other way. Meter per second squared. Which means it's decelerating and then speeding up in the backwards direction. So we're definitely accelerating. Okay. What's the displacement of the entire trip? I'm going to tell you right now it's 0. But the way to find displacement, remember, find displacement from a velocity time graph, that's the area. Okay? So all the area that we have here, and this area down here, right? Area is displacement. And the reason behind that, because the calculation you're doing length times width. The length, which is velocity, times width, which is time, v times t, is equal to d. Right? Now this area up here is positive. This area over here is negative because it's below the x-axis. And you can notice that they're very symmetrical. I can find out all these little areas, like these little triangles and stuff if I wanted to, but I noticed that they're both exactly the same. 7 seconds on the bottom, right? 1, 2, 3, 4, 5, 6, 7 seconds on the top. Yeah, looking pretty good. And this here, there's little triangles in here, but they're both the same, top and bottom. So they'll add up to 0. Area under the graph. Okay, let's keep on going here. Let's use the following information for the next 2 questions. We've got hamsters sitting on a shelf that's 1.78 meters above the ground, and one of the hamsters decides to fall off. Right? So what we know is that the hamster is going to fall a displacement of negative 1.78 meters because he's falling down. Acceleration is also down at negative 9.81 meters per second squared. Since everything's moving down, I could just say these are both positive numbers and just say down is positive. If you want to keep the negatives, you can. Because they fall, it doesn't get thrown off the shelf. Because it falls, my VI is going to be 0. Right? It's not being thrown down. And we're just going to try to find time. So what formula do we have that doesn't have VF, right? So VF is not in here. So when we're talking about accelerated motion, we've got to deal with those 5 parameters, with those 5 variables, right? VI, VF, A, T, and D. There's 5 of them. And all formulas only involve 4 of them, which is nice. So, what formula would I use? It looks like I'm going to use the delta D is equal to VI T plus 1/2 A T squared. So it looks like I'm going to be using that formula there. Solving for T. What's nice about this is that since VI is equal to 0, this whole first term is also equal to 0. All right, so that first term's gone. Then I can start rearranging this. I'm going to times by 2 to get rid of the half. That's my first thing. Times 2 on both sides. And then divide by A on both sides to get rid of the A. And then I'm just going to take the square root of both sides. That last step here. And we're going to get T here. You notice that I modify the answers. So if you got one of the earlier versions of this, I'm sorry, but I had to modify them. Because the answer was originally not there. I must have had a different version or different number in the test, and I forgot to change the answers. Maybe they had a different height. Maybe I typed something wrong when I was making the distractors. Yeah. So 6.02 seconds. How fast will it be when it hits the ground? Okay, so VF, question mark. I'm not going to use the time, right? Because the goal is not to use something that you found, because what if you don't trust it? So we just have to figure out something else that doesn't have time in it. So that looks like it's going to be the VF squared is equal to VI squared plus 2AD. I have all the other stuff here. Don't even have to rearrange it. VF is just equal to the square root of VI, which is 0. So that's nice. Plus 2AD. So 0 plus 2 times A times D. Make sure to take the square root of that answer. Notice that one of the answers is there if I forget to take the square root. But the actual answer is B here. 5.9096 meters per second. Cool. Dog is running around display. We just have to find out one of its components. So dog runs a certain angle. So 29 degrees northeast and never eat. So it's in somewhere in this quadrant. Right about here. I'm just trying to find out what the scale of this picture would look like. So that's 18.0 meters. So the angle, because it says east of north line. So the angle is actually going to be in here. It means I'm going to go north, then I'm going to go east, this many degrees, right? So I go north first, so I'm actually going to draw that in there. North first, and then I go east, and my angle is 29 degrees. So I want to determine what the north component is. So if I'm going to use the 29, the north is going to be the adjacent side of this, right? That's my y component. So I'm going to be using, because usually on this like standard position and most other angles, we usually use sine for that part. In this case, we have to use cos if I'm going to use the 29 degrees. I can draw the triangle the other way and find the other angle, right? Just make sure your calculator now is in degree mode. Type it in and you should get 15.7. Alright, so acceleration due to gravity, 8.96 meters per second. That's pretty close to Earth. See this on Saturn, right? Yeah, 8.96 meters per second squared. How much time would elapse if you threw an object up and it fell back down to the surface? So I'm assuming it comes back down to the same height. So it comes back down to the same height. Let's just say that d is 0, right? The acceleration, which we know is downwards, that's negative 8.9, what is it now? 8.96. What else do we know? Vi, we know Vi, sorry, is 5.00 meters per second upwards. Okay, so that's why that's a positive number. And we're trying to find time, right? So I can use d is equal to 0. We do run into some problems with that formula. If I say d is equal to 0, we might run into some issues, right, depending on which formula we use. Or because it comes back down to the same height, so it goes up at 5 meters per second, it's going to go around, come back down at 5 meters per second, but this time a negative number. So technically, because it's the same height, I could say that my VF is also a negative 5. If I'm making the assumption it comes back down to the same height it was thrown, it's negative 5. So actually I can use any formula I want that has a t in it because I have all the information. Probably just wouldn't use the one where you're saying times by t or something like that. It's just kind of, or times by as 0, so times by d, because I don't want to end up getting 0. So let's pick one here. So let's say A. Let's do that one. Let's do delta V over t. Remember, delta V stands for final minus initial. And we have our final, negative 5. We have our initial, plus 5. So I'm going to minus a positive number. So I have two negatives there. So it's not going to be 0, which is nice. And we're going to divide by, delta t, which we don't have. So actually I have to rearrange for delta t, which I didn't do. So it's going to be negative 5 meters per second, minus 5 meters per second, divided by A by negative 8.96 meters per second squared. So we get negative 10 divided by negative 8.96. So two negatives, which is nice. ends up being a positive number. So, pull my calculator. 0.96, sweet. 1.12 seconds. Because that extra decimal round in there. Okay, consider the object is thrown up. What's the max height? Okay, so let's go through. So we're trying to find d in this case. It's not going to be 0 because now it didn't come back down. So we're just at the top now. It hasn't come back down, so we're just at the top. We're trying to find out what that is. The acceleration is still the same thing. Okay. Squared. VI is still the same thing. That's upwards, acceleration is downwards. And we're trying to find, it's like I can't use time because we're at the max height. Because we're at the max height, we could say VF is equal to 0. Remember, it's coming up. It's got to stop for a bit, change direction, and then come back down for a bit. Like you won't even notice it stops. But it's got to change direction. If you have to change direction, you got to stop. So there's what we have. What formula would we use? Oh, yeah, okay, that makes sense. It's going to be that one. So VF squared doesn't have time in it. So again, I'm not using the time because it's something I found in a previous question. If I don't trust it, I'm not going to use it. But I couldn't use that 1.12, right? I'm going to have to actually do something to it. Use all the decimals. And I'm going to have to divide it. Right? I'm going to divide by 2 to make sure I get the right answer. Because that's the full time, but the halfway mark is at the top. So you have to divide by 2. Anyway, we're just solving for. So I'm going to take the VI, I'm going to move that over. I'm just going to move that over. I'm going to divide that by, what is that for? D, so 2A. There you go. You notice I'm not really putting all the numbers in. These are just multiple choice questions anyway. So we got negative, so we get 0 squared. You put that in whenever you want to. Minus 5 squared, so my VI squared, divided by 2 times 8.96, not 9.864, 9.81, sorry. So we get a height here, divided by a negative number. So negative turns positive, so 1.3950. But the 9, because I want 3 sig digs, so the 5 is going to round up to the 9 rounds up again. So we get 40 meters. It's a positive number, so it makes sense. Let's one up. All right. Let's see what else we have here. Oh, it rolls over. So a car will roll over if it's going too fast around a curve, mostly because of the tendency for the vehicle to move forwards, right? So what's going to happen is like when a car starts trying to turn, the undercarriage part will turn, but the top will want to continue going forward. So if it's going along on top of each other, and this starts turning, but the other part starts going forward, it's going to start rolling over itself. It's kind of like being tripped over itself there. So the tendency for the car to move forward. The top of the car still wants to move forward while the bottom of the car is starting to turn. So you get this kind of leaning effect. Don't go too fast. An object will continue to remain at rest or move at a constant velocity when F net is equal to 0, right? There we go, equal to 0. Let's use this first law, all right? So you'll continue to remain at a constant velocity. Should probably change that word speed, but a constant velocity unless acted on by an external net force. So my net force is not 0. External non-zero net force. The force of friction that opposes the intended motion of an object is called, opposes the intended motion. So assuming we're not moving at this point. So I'm going to say that's my static friction. So I'm not moving yet. If it is moving, it's opposing the motion as it already has, and then that's kinetic friction. The coefficient of friction is just the relationship between the normal force and friction. It's just a way to say that if you increase the weight on the object, the friction is going to increase as well. It changes dynamic material you're on. An applied force of 240 newtons causes a ball to start moving horizontally across the lawn if the coefficient of static friction is law. What is the mass of the ball? Okay, so based on what we have here, it says it causes the large ball to start moving. So I'm assuming that force is like the breaking point, because static friction is stationary, right? This is like the coefficient of static friction, which calculates the maximum amount of friction required, right? So I'm going to say that to get this to start moving, that force applied has to be equal to or be just a little bit more than the actual static friction there. And then the ball will start moving. So this 240 is just got to be a little bit more than the actual friction. So let's just say it is equal, but maybe it's just a little bit, just a tiny bit more. But we're just going to say they are equal because it just started to move here. Right? So there's friction. So let's use that knowledge, and then we're also going to use the knowledge that our FG on a horizontal surface, that my FG and my FN most likely will be the same magnitude. They're going opposite direction, but they'll have the same magnitude. Assuming these forces are not like at weird angles, right? If I push down on the ball, the FN is going to increase. If I kind of pull up on the ball a little bit, the FN will decrease. FG will stay the same, but FN will kind of change depending on the other forces there. So what we could say is that FF, because I was talking about this in the previous question, is related to Fm with this static or coefficient of friction which we have here. So mu is 1.6. All right, so let's put some stuff that we know in here. So what do we have to find? We're trying to find Fn, which is going to be equal to mass times gravity. So Ff, which is equal to mu m times g, and I just have to solve for m now, right? So we decided our force of friction is going to be 240. We got gravity, 9.81. We got mu. Remember, this formula is all about absolute values anywhere, so I'm not too worried about the directions and the sign convention here. Remember the formula, it's above my head somewhere. But there's absolute values in the formula. So I'm going to rearrange this for mass. So divide both sides by mu and g. There you go. All right, so we got 240. We're going to divide by 9.81 and the 1.6 number. So we get D here. So we get 15.2905 kilograms. There we go. Cool. Okay, a circus performer with a mass of 140 is flung from a catapult. Its peak of trajectory, it's moving horizontally 50 meters per second, and he is 300 meters above the ground. With the ground as a reference, so that's good. What's the mechanical energy? So remember the reason we need a reference point, because our EP, which is calculated by going mgh, really depends on where you're measuring from, right? You could say the EP is 0 at the top if you wanted to. But we also, EM is also equal to EP plus EK, which is 1/2 mv squared. That doesn't need a reference, but we need the reference for the mgh part. All right, so we got the M. I'm assuming this circus performer is on Earth, so 9.81 sounds like a good number to use for gravity. And it's 300 meters above the ground. So right now we have 412,020 joules of that energy, and we're just going to cross that one off, and that's way too small. I'm just going to cross those two off. Because now I have to add in the kinetic energy. 1/2 mv squared. So I've got to add in this extra 1,075,000 joules as well. So if I add those two numbers together, we get 587,020 joules. So that's going to be A there. So remember, mechanical energy is going to be the sum of those two types of energy. Actually, all the energies, but usually we just talk about like the ones for physics, potentials, like gravitational and elastic potentials and kinetic. All right, Mercury is the closest planet to the sun. The second closest is that. What's the magnitude of the gravitational field strength on this planet? Oh, it's the second smallest planet. It has this blah, blah. Okay, so they're just asking us, what is the G, right? On Earth, it's 9.81. On other planets, we're going to have to calculate it, right, using the planet's mass, how far away you are from the planet, the center of the planet. So if you're on the surface, you're just the radius away, right, of the planet. And we got G, we got 6.67 times 10 to the negative 11 number for mass there. 3 point. Sorry about my cursor, it's just going to go wild on me. Now just make sure you square the right numbers there. Type it all in your calculator and you should get a pretty reasonable answer here. It's a pretty small mass. But it is Mercury, it's a small planet. And I get 3. I think I talked about this. Oh, actually, for some reason I thought Mars was 3. But Mars is maybe a little bit bigger. Maybe it's a 6 or something. Those are not right unit. Technically, those are, you can use those units. Because we're talking about gravitational field strength, we got newtons per kilogram. Because the object is not really accelerating. We could drop the object, it will accelerate at that rate. But it's not accelerating, it's just in a field, we just say newtons per kilogram. The radius of the Earth were to double, how would it affect? Just double? How would it affect the gravitational field? It would be a quarter of what it was before. So you have to remember that. Gravitational field. Okay. Next time I can use the right one, I'm just going to use F there. So my old number, which is going to be calculated by going GM over R squared, remember that's just 9.81, right? So if I ever see this, that's my old number, it's 9.81. So my new number is now we're going to take my mass, take my radius, and I'm going to double it. So that's going to turn into GM over 4R squared. So you've got to take that 2, pop it out of there, and then you can see here, all of this, that's all my old number. The 4 is in the denominator here, so that means I have a 1/4 of my old number, right? So that's what we have here. So that's, why it's a quarter. Just go back down here. Sorry. Too far here. In 3 minutes, okay. Cruising along in this practice deployment. So I got a quarter. Oh well, let's do 4. All right. A thunderclap is often heard from lightning strikes that are short-lived but very loud. The sound can be described as a longitudinal. Now, sound is a compression wave where the air kind of compresses. So imagine my air in the middle here. Get rid of my hair. It's going to compress. Okay, let's put this hand. Let's put this hand in the middle. There's better. So it's going to compress that wave. It's going to push the other wave, and it's going to compress and push and press and push all the way down. So that's going to be longitudinal. And lightnings are huge claps, so really loud. So we're going to say loud amplitude. Okay, the moon Ariel orbits Uranus and has an average radius of this, and Uranus is moon Titania, orbits at this radius. What do you expect the period to be? Okay, so just want to double check something here. Sometimes it's nice when you think, oh man, if I compare my two numbers, oh, this one's like twice as big as that one, or this one is something else. No, but that's not as nice. It is bigger, but it's like 2.28 times larger, which is not going to help us solve this question. Well, it could, but probably the best way to solve this question is think about what did they have in common. All right, so we have Uranus here, right, and then we have the two moons, varying radiuses in different periods, right? But what they have in common is Uranus, right? And that's what they have in common. They have different periods, they have different radiuses, everything else is different, but what they have in common is what they're orbiting. If I can find out what that is, because that's what's determining how fast they're moving, essentially, around this, and where they are moving around in the orbits. If I can find that, I can use it in the other question. So let's start off with the information we have. So this is for Ariel, because I know all the information about Ariel. Okay, so what I'm going to do is I'm going to start off like we usually do. There's only one force holding this in orbit. That's gravity, right? The forces of gravity are different too, because they're different distances away from the planet as well. So I can't say that's in common. That's a different thing. And then we go mass times acceleration, mass times gravity. We cross off those masses. Then we decide which formula to use. Since we have period, I'm going to use the 4 pi squared r over t squared formula. I'm not giving myself a lot of space here. Now g is not 9.81 because this is not Earth. So we have to calculate what it is. All right? We can actually calculate it. We have the information. No, we don't. We don't have the mass. But if we did, we can calculate what it is. Because we don't have that, and the reason we want to use it, because I need the mass to do the same thing over here, right? So if I want to find the period, it starts out the same way. So AC, M's cancel out. We got the same place again. Right. But this time, on this side over here, we need to find the period. So if I rearrange this, I'm going to times the t squared up and start moving everything around here. Here I have to like times by r squared times by r squared. Notice that it's going to cancel out those. I'm going to combine the cubes, those together. And I'm going to start moving things around. Divide the GMM down. So what I need is I need the radius, which we have, but I need the mass of Earth, or the mass of whatever you're orbiting. Because the other stuff cancels out, this planet mass cancels it out. So I don't need the mass of those moons, sorry. But I need the mass of Uranus to do this question. So then I can take the square root and find out what my answer is. But this is important, I need this. That's the mass of Uranus. Ha ha ha. Right, so that's what I need. So I need to go over here and I have to solve for that mass. So I'm getting a mass here by itself. So I got 4 pi squared r cubed over GMT squared. So I just divide down the GM, times up the, oh, I don't even, sorry, not the M. I don't have the M. Yeah. If I did have it, which is going to be given to you, it's like I have this sheet here. So you're probably not going to expect it, but this is supplementary information you're going to need for one of the questions on the test. All right. You'll see why when you get to that question. But if I don't have it, this is how you're going to have to find it, right? So you're going to have to find it using the information of one of the moons. Now there's another way to do this, but technically I'm not supposed to or needed to teach you the other method. The other method uses Kepler's law, where we know there's ratios are consistent for things. It's just we glance upon it in our notes, but you don't need to remember it. So. Okay, so we get a mass for Uranus here. 8. This is the big question just for one multiple choice here. And then I got to go over here to plug it all into that one. So I got my calculator. So I got 4 pi squared times the correct mass. So I use the other mass now. This is the titanium's mass. Or not mass, radius. Cubed. So the power of 3. And then I'm going to divide by G. And my mass. I gotta make sure it's the square root. And then take the square root. So I hope I get one of the answers over there. I do, I get A. So I get 751,858 seconds. And then that's going to round nicely. Not really round nicely. It's going to give me 3 sigdigs. It's further out. So I expected it to have a higher period, but these all have higher periods, so that doesn't help us. Okay, a planet orbits a sun with a certain mass once every this. So what is the radius of that planet? So it's very similar to what we did up here. Now we're solving for R, right? Okay, so we get FC, let's go FG, so MAC, MAG, okay, cross out the masses of those. That's the mass of the planet. Oh, excuse me. And then because we have periods, we're going to use the formula that has period in it. And we don't know this G, so we can find it because we have the mass of the sun, so just give this to us. So what we can do is rearrange this for period, right? So we're going to times the t squared up to the other side. All right, so now we have the t squared over here. So times the both sides, cross that off. And then I'm going to move everything else away from that. So I'm not showing all the steps. I'm showing the important one. You have to times the t squared up, and then move everything else down to the other side, or up to the other side. So timesing that r squared up and taking that and dividing it down. Okay. And then our goal is we're looking for what? Oh, what is the radius? Okay. Should have caught myself on that one. That seemed too easy. Okay, let's restart. So 4 pi squared r over t squared. We're solving for r. That's what I messed up on. No, r squared. So we got to times both sides by r squared. Right? You get the r squared out from the denominator, but then you realize, oh, I get r cubed over here. So it's 4 pi squared r cubed over t squared equal to gm. And then I'm going to start moving things away from the r here, right? So all that and dividing that down over there. And then we get t, or not t. It's getting a bit late. Okay, so we get r cubed, that's a cube, is equal to gm t squared over 4 pi squared. Then we got to take the cubed root of both sides. All right, pull out your calculator. 6.67 to the negative 11 times the mass, 1.2 times 10 to the 32 times the period, 5.2 squared. Okay, divide by two numbers. Make sure, remember, when you divide it by two numbers, you're careful about how you're dividing those two numbers. Then we got to take the cubed root after we're doing all that. So take the cubed root. I know you can't see what I'm typing in. Hopefully you get the same answer. Remember, find that cubed root button. That's in the math section, right? So my radius is 8.296 times 10 to the 13 meters. Blam. Doing pretty good. Okay, a cannonball is shot horizontally off a cliff. That is 96 meters above the lake. When the cannonball lands in the lake at a speed, it has a speed of 284. What's the kinetic energy when it left the barrel? So we've got to think about the energy transfers here, right? So at the top of this system here, so at the top of the lake, assuming that we're measuring it all down to the bottom of the lake here, so here's my lake. At the top here, the cannonball that got shot out of my cannon, it has two types of energy. It has mechanical energy, which is going to be EP plus the EK that it has to start off with, right? But the EP is really dependent on where you're measuring from. So, so right now we're 96 meters above the ground. So we're going to have some EP here. But when it gets to the bottom and splashes into the water, that's not very parabolic. I'm going to redo this. When it splashes into the water and goes splash, splash. Down here, it's EM. It's still EP plus EK, but that's zero because it's measuring to the ground. The height is zero, so that's gone. So really, the only EM I have down here is kinetic energy, which I can calculate going 1/2 mv squared. So let's just calculate that really quickly because we had that information. So 1/2 times the 4.2 times the 284. This is the speed at which it hits the water at. It's going to hit the water at an angle, but I don't really care about that. I'm just worried about its speed when it comes to this formula anyway. So at the bottom, it's got 169,377.6 joules of energy. Well, that means it had that much energy to start off with, but it was kind of split between two things. It was split between the EP and the EK. So this here, let me just put an arrow here. This here is, let me just redraw that arrow. Oh my lord. I'm going to erase that. Okay. This here is the same as that, right? The same as the sum of those two pieces, because the EMs are equal to each other. So this is equal to 1,690, 377 joules. Okay, but at the top we have two types of energy, right? So we got EP, which is mgh, and the 1/2 mv squared, right? Or in this case, we don't have to find the speed. Maybe one of the questions would be find how fast it's moving, but we just have to find out what that EK is. So if I look at the mgh part of this, 4.2 times the g, 9.81, times the height, 96. So 3,955.392 joules is EP. How much is EK? Well, it's what's left over. So we know the total is 169,377.6. If I minus over the other answer, I find out that this is 365, right? I'm going to take this number, minus it over, right? Minus. So we find the EK to be 165,422.2 joules, which rounds to B there. Cool. All right, quartz crystal here oscillates at a simple harmonic motion at 10,000 kilohertz with an amplitude of a very small amount of millimeters. So we got to watch out here. Kilohertz is not the proper unit. It's got to be regular hertz. So my frequency, which is 10,000 kilohertz, is, 10 kilohertz is 10,000 hertz, right? So you get rid of the k times by 1,000, or times by 10 to the 3, because that's what the formula sheet says. You forget what that is. All right, so it's a really big amount of hertz. And my amplitude, my A, my maximum stretch, should be meters, because you look at the units there, they say 1 meters per second. So this is going to be 0.05 times 10 to the negative 3 meters, which I think is the negative 5, if you were to calculate it. Yeah. 5 times 10 to the negative 5 meters. Okay, so we got all that. Then we pull out our formula sheet to find out our speed. Okay, but most of our formulas don't have frequency in them, so we're going to have to change this to periods. Remember, a period is 1 over f, so it's going to be a really small number. It's going to be 1 times 10 to the negative 4 seconds. Okay. And then we have to find our max speed formula. So one of our max speed formulas says that I can take 2 pi r, or a, sorry, divided by my period. Because oscillatory motion and circular motion are very closely related to each other, because 2 pi r is the circumference of a circle, and 2 pi a is just kind of relating it to this kind of back and forth motion of an oscillating crystal to a circle, which is kind of weird, but it works out. Okay, and I'm going to divide it by my period. And then you notice you get 3.14. It's pi. It just mathematically ends up being pi there. Meters per second. It's pi meters per second. Okay, cool. Mr. Allen is standing inside an elevator. Physics students come and disable the safeties and cut the cables. Mr. Allen has a mass of 75 kilograms before he entered the elevator. What is his true weight? What is his mass and true weight as he undergoes free fall? So my true weight, remember your true weight is never zero unless you're like in a place where there's no gravity, but I'm near Earth here. So my true weight is always going to be Fg. Fg is my true weight. That can change depending on where you are in the universe, which planet you're on. But if we're talking about Earth, that's just 75 kilograms times 9.81 newtons per kilogram. And what do we get? 75 times 9.1, so we're talking about true weight. We get, yeah. And even though I'm free falling, my apparent weight might be zero, right? Because remember, apparent weight, it might pop up later. One of these questions, I can't remember what these questions are. My apparent weight is Fn, right? That might be zero. My true weight is always something, even if you have gravity around you. And you always have mass, right? You can't lose your mass. Mass is your mass. So you have to have a mass of 75. So you kind of cross out this, like, I'm in free fall, right? Free fall, it seems like I'm weightless. But my apparent weight might be zero. Because at that point, there's no abnormal force. You're falling at the same rate as the elevator. You're not pushing on the elevator's not pushing back on you. So you just feel weightless. Okay, Zach is on a toboggan here. He's sliding down a snow-covered hill. Has a mass of that and a slope of 30 degrees. Draw free body diagram. Calculate the perpendicular and parallel. Assuming no friction. What's the acceleration if there's no friction? Okay. So let's see what we have. So I'm just drawing my picture. 30 degree angle. 30 degrees. So I got there's my sled with Zach on it. We got a force straight down. Well, that's gravity. We have a force perpendicular to the surface that we're on. Okay, so we're being very specific. And that's it. If there was friction, there'd be a force going this other direction that's parallel to the surface that we're on. That ends up being 90 degrees to the surface. But that really doesn't exist. Right? So those are my two forces. What are the pairs that... So free body diagram does that. And then what are the parallel and perpendicular forces here? So I can draw in the component pieces. So my parallel and my perpendicular pieces here. In class we called them the fx and the fy, but we can call them the parallel and perpendicular. So my parallel piece, that's my fgx. That's parallel to the surface. My perpendicular piece, that's my fgy. Okay. So if I look at my picture here, we got 30 degrees. So I need Fg. All right, so to do this, I'm going to have to find out what Fg is, which is just mass times gravity. 700 times 9.81. 6,867 newtons. Perfect. So now I can go down here and find out these two. So Fgx looks like it's the sine. So I'm going to go Fg sine 30 degrees. And this one looks like it's the adjacent side, so that's going to be cos. Fg cos 30 degrees. Okay. Well, sine 30 degrees is a half, so that's pretty easy. So my Fgx here is going to be 3.43 times 10 to the 3 newtons. Then my Fgy is going to be the cos version of this. So times cos 30. So 5.95 times 10 to the 3 newtons. Okay. What's the acceleration now? So if you look at this picture very carefully, let me just redraw this again. We got our forces right there. Fn, normal force, gravity. So what we know about these two forces here, the FGY and the FGX, well, the thing about the FGY, it's going to cancel with the FGN. They're going to be the same magnitude but in opposite directions. There's no other forces, not like they're pushing down into the hill like someone else is doing that, or someone's lifting it up off the hill. So these two forces are going to cancel each other out because all we're doing is just sliding up and down the hill. So the only two forces we have are the ones that are going up and down the hill. So my F net in this situation is the sum of the forces, but F and FGY cancel out. It's just FGX. That's it. We don't use FG because we broke it up into its pieces. We cancel out a piece of FG, it's gone. Right? So we don't actually use FG in our calculations. We only use those perpendicular pieces there. So my F net is, that FGX is up here, so that's that 3,000 number. And that's just from the top of there, 3,003.5 newtons. Remember, your acceleration is going to be F net divided by mass. So I take my F net there and divide it by the 700, and we get 8.50 meters per second squared. Cool. And it has a direction, downhill. Downhill. Kind of awkward. Okay. Next one. It's a dirty section. Now we have friction, right? So if I were to draw this picture out now, same picture, box is going to change its shape, and the angle keeps on changing a little bit. Now what we have is friction. So FF, that's going to try to slow us down there. It's perpendicular to our other. Alright, so let me just draw out some things here. Got FGX, got FGY, the FGY and the FN cancel each other out, but they're still there. The forces don't just disappear. They are still there. That's why that's important, is because when I do my F net, which is going to be FGX plus this FF now, we have to find out what FF is. To find out what FF is, I need to know the mu, which I have, the coefficients of kinetic friction, and the normal force. Remember, we already calculated the normal force. The normal force, we're making this assumption that this normal force and FGY are the same number. Right? This is the same thing as FGY. The magnitude is the same as FGY. So I calculate the force of friction by taking the FGY and multiplying with my mu. Because we're making that assumption. It's a good assumption. So 5,946.99. You know what? I messed up on the previous question. That number's not right. I'm looking at my calculator now. I'm thinking, what is this? Oh, This should be 4 point up here. My bad. Oh, you guys should catch it. It's a good thing I'm looking down my calculator. I'm using someone else's calculator here that can see all the numbers and what I'm doing, which is kind of hindering what I'm doing here, but because I would have just typed the number in last time, which would be. Okay, so I'm going to take this number, I'm going to times it by 0.3. So there's my force of friction. My force of friction is 1784.0989 newtons or so. That's my force of friction. So I'm going to take that and put that over there. So my F net is now my FGX, which was at 3,043.5 newtons. Now I need a sign convention. I'm going to say downhill is positive because that's the force downhill is bigger than the force of friction here. That means my FGF is a negative number, 1740 newtons. So my F net now is a bit smaller than it was before. 1649.4 newtons. And then I can find my new acceleration, my F net divided by my mass. That's 700 again. So my acceleration now is 2.36 6 meters per second squared. Down. Good. That's the Jackson right there. Okay. I'm just going to hit save on this file. Be right back. Okay, so I'm back. So our next one here, oh, we got a few more questions, right? Well, not too many. We've got a page and a bit. All right, next question here is trying to determine, based on this picture, what is the kinetic energy of the 1 kilogram block just before it hits the ground? Okay, so let's see what we have at the top here. So we have this 3 kilogram mass on a frictional table attached to a 1 kilogram mass vertically suspended system. It's released from rest. It falls to the ground 1 meter, pulls it down. It pulls the frictional system. Okay, so what's the kinetic energy of the what? The 1 kilogram one again? The 1 kilogram mass. Okay. Okay, so to do this, we got to figure out, okay, so what's the energies of everything going to be at any given point here, right? So at the very beginning here, it's at rest, right? So let's measure everything with reference to the ground. So this is going to be my reference down here. Right. So my height is 1 meter. So to start off with, this is the start. Everything's at rest, so EK is going to be 0. So my EM, my EKs, I'm going to have EK for the 3 kilogram guy. I'm going to have the EK for the 1 kilogram one. And I'm going to have the EP for the 1 kilogram one. Now, the reason I'm not concerned about the EP of the 3 kilogram one, because it's not going to change. It's going to slide across, so the EP is not going to change, but its EK is going to change. All right? So at the beginning here, this one's 0, it's not moving. This one's 0, it's not moving. So all I have is this MGH of the 1 kilogram block. Right? If I want to include the 3 kilogram block, I could, but it doesn't change. So when I do some minusing stuff later on, I'm just going to minus the number from itself. Right? So 3. So 1 kilogram times 9.81 times 1 will give me 9.81 joules. Okay. Okay, so that's the total energy we have to start off with. So as everything starts moving around, this block here is going to now come to the ground, right? It's going to slam down this 1 kilogram block. It's going to move downwards. It's going to have a velocity as it hits the ground, right? So it's going to be down here now. This 3 kilogram block is going to be over here now. Kilogram. Yeah, kilogram block is here. And it also has a velocity, which, according to physics and attached by stuff, these two velocities are the same. That's going to be useful for later, so I'll probably get rid of those eventually. But they're both going to be the same, right? Well, I might have to find out what they are. Maybe. We'll see. Maybe I don't. I'll figure that one out a bit. And when it hits the ground, its EP is going to be 0. So at the end over here, let's go through this again. So my EM, which is going to be the same as in 9.81, which is kind of nice. My EM is going to be my EK of my 3 plus my EK of my 1 plus my EP of my 1 now. But now this one's 0, right? Because now I'm at the ground, right? That one's 0. But the other two I don't know. So 1/2 M. Now this M is 3 times the mass of the other one. Now this is where I'm going to have a little bit of fun here, right? You might be thinking, what is Mr. Allen going to be doing here? I'm trying to avoid kinematics as much as possible. So this is going to be 1/2 3m's v squared, and this one's just going to be 1/2 mv squared, because this other mass is 3 times the other size, and plus 0. Okay. So what I'm going to do, this plus 0 doesn't really do too much. What I'm going to do here, if you notice that 1/2 mv squared, that is the kinetic energy of that 1 kilogram block. And this other one is 3m. So if I move the 3 out to the front of this, you'll notice that this is just 3 times Because I have 3 times the mass, which means I have 3 times the EK. So this is 3 times 1/2 mv squared plus a 1/2 mv squared. So if I were to factor something out of this, what you would notice is that actually I don't even have to factor anything else. This is going to be 3 EK1s plus an EK1. That's 4 EK1s, and that's equal to 9.81. So if I want to solve for EK1 now, I just take this, divide by 4, divide by 4. So EK1, the killer or the EK of number 1 there is just a fourth, because it's got to split between all of them, and the other one is going to have more of the energy because it's more massive. So this is only 2.45 joules. Now that's a very hard question, right? So I don't know. There's other ways to do it. You can find out how fast it actually is going. You do that math and actually do that, and then 1/2 mv squared. Nothing wrong with that. And I just wanted to avoid using kinematics here. You have to find the acceleration. It's going from rest. Find the final speed, then 1/2 mv squared. Then do that, right? That's one way to do the question. Or you could do it this way, right? Let's see if I can do it the other way. Right? Got a little bit of time. Do I? A little bit of time. Let's see if I can do it the other way. Let's see if I can find out how fast it's going. So the first thing I need to figure out is it's on a frictionless surface. What is the F net, right? So over here, if I were to draw my free body diagram, we have gravity, which is mass times gravity, which is 1 kilogram times 9.81, 1 kilogram times 9.81 newtons per kilogram. So this is going to be 9.81 newtons. Just coincident because it's 1. Then we got some tensions in here, right? So we got a tension upwards. We have a tension over here that way. Those two tensions are the same. But if I need them to cancel out, because I want to do my F net calculations, I have to do the whole bubble, right? So I have this system right now, it looks like this. And I have these two forces. This is 9.81 newtons. Then we have tension, and then we have tension. I need to look at this whole picture to make sure those tensions cancel out. Because if they don't cancel out, then I'm going to have some problems, right? I need those to cancel out. They're gone. So, my A is going to be my F net divided by my mass. My F net is going to be this 9.81. That's the only thing that didn't cancel out. And my total mass, 4 kilograms. It's kind of looking familiar, doesn't it? Because of kind of what we did up there. 9.1 divided by 4. So my acceleration is 2.41 meters per second squared. Now that's not my answer, right? It just happened to be the same as that answer up there. But we're going to keep on going. Now, it's going to accelerate at this rate downwards. Accelerating downwards. It's going to go down a displacement downwards of 1 meter. And it has an initial velocity of 0. We just have to find out what that final velocity is. So what is that final velocity going to be? So I need a formula that involves this thing. So that's going to be the VF squared formula. F squared formula, VI squared plus 2AD. I'm going to rearrange this for... Oh, I don't have to rearrange it. Just take the square root of both sides. That's pretty nice and easy. Okay. So what's my VF here? So 2 times my A, which we just found, times the D, which is just 1. So we get that, and I got to take the square root of that answer. So my final velocity of this situation is 2.21, etc., etc. 2.2147 meters per second. Then I can take that up here and find my EK, 1/2 mv squared. So 1/2. My mass is 1 kilogram. My V is 2.2147, a bunch of decimals there, squared, because I'm doing the EK just for the 1 kilogram block. So times by 1, times by this number squared. Oh my lord, we get the same answer. 2.45 joules. So I confirmed it. Both those ways worked. I don't know which way is the easier way. This way is more logical. This way was just more fun. We're talking about energies. This way we're talking about kinematics. Both ways work. Cool. Train is whistle. What is the speed of the train as it approaches the man? Okay, I always like these questions when you're rearranging these. Okay, so we got the man hears. So that frequency is what we hear. So 474. We got a source frequency here. Oops, I hit the button. All right, so we got a source frequency here of, let's go black again, 435 hertz. So the frequencies won't come up, so that means it's heading towards you, which is already nice. We already knew that. Remember, towards is negative. Frequency, the pitch is going to go up. The speed of sound. And the speed is the source that we're trying to find. You notice that the source is S. The speed of sound is without the one without anything on it, which kind of confuses some people. So we're trying to find out what this is. Okay, so let's go move this down on this because I'm going to do some rearranging. So F. Now we got these big brackets, and the formula goes like this: V minus Vs. We pick minus because it's moving towards it. Fs, right? So we're trying to find this Vs. It's in the denominator. So probably the best thing to do is kind of split the top and the bottom into their two respective set of brackets. Right? Fs. Okay. Then I got to move this bottom piece to the numerator, right? Because I can't solve for something in the denominator. So we multiply everything up. It's in the denominator up to the other side. The Fs is not in the denominator. It's like technically over 1. It's going to sit in there on the side, but it's in the numerator actually. So it's kind of happy where he is. But I got to take this whole bottom piece here and times both sides by V minus Vs. Something you'll learn in, oops, not on that side. Something you'll learn in rational expressions in Math 20. Okay. Now my next goal here is to, I don't know, get rid of these brackets. So one thing to do, maybe divide the F down to both sides. So if I divide both sides by F, divide by F, cross off, divide by F, they don't cancel out because they're different Fs. And then my last-ish step here is the minus over that V. I'm going to leave the negative Vs on that side. I'm going to take the VFS, F minus V. We're going to deal with the negative later. So right now we have V and negative Vs. I can just put all the numbers in now. We're going to end up with a negative number, hopefully. If we don't, then we did something wrong. So 330 times Fs divided by that other number, 474, minus V again. So we get a negative 27, which is good because we have negative Vs is equal to negative 27, which means Vs is a positive number. It's 27.2 meters per second. That's probably one of the harder ones to rearrange. Not too bad, not impossible. Let's go. What's the magnitude of the acceleration of this? We have friction between the blocks and the table. Yeah, okay, this is not too bad. We kind of did a question just like this up here. All right, so we have all these forces. I'm going to start drawing all these forces in here. So we got gravity. We got normal force. We got gravity. We have tension. We have tension. This tension and this tension are the same. Well, same magnitude, but opposite direction. And then we have friction. So there's my picture. So if I look at everything here, put a little box around everything. The reason I'm going to look at everything to find the acceleration is because I need some of these numbers to cancel out. I need this tension to cancel out with this tension. These guys already cancel out automatically anyway. So what's left over here is this gravity of just the M2, now 10 kilograms. So that's going to be the 10 kilograms times 9.1 newtons per kilogram So that's going to be 98.1 newtons. Okay. And then we have friction over here, right? So this friction here is 20 newtons. So my F net is the sum of all these forces. I need a sign convention here. Let's just say down that way is positive, that way is positive. So then we're going to have 98.1 newtons minus this 20 newtons that's inside the circle here, right? So we get 78.1 newtons. Now I want to find my acceleration. We take our F net divided by my mass, and because we put a circle around everything, in this situation we're including the 20 on this block, we're including the gravity from this block, we have to include all the masses, so we're going to divide by 40 kilograms here. All right? So I get an acceleration of 1.95 meters per second squared. It's more of like a magnitude here, right? Very good. Almost done. Oh, yeah, we are. Cool. Okay, so our goal in this one, find the coefficient of friction. So that's at mu, right? So to find the mu, we're going to need two things. We're going to need to know the force of friction and what is the normal force, right? Now, it's on, I'm assuming on a horizontal surface here. Yeah. We're on a horizontal surface. Gravity and the normal force will probably balance each other out. Assume these other forces, it's given a push, and maybe it's just push directly sideways. These two forces here will balance each other out. So Fn and Fg have the same magnitude. Opposite direction, but same magnitude. So if I go mass times gravity, I'm going to find both those numbers. Both the magnitudes. So I get 14.715 newtons. Okay, so that's half my battle. Now the next part is to find out what the friction is. Okay, it's going to come to a stop. So there is a friction force here. All right. And after I push it, I'm going to not push it anymore. Eventually it's just going to come to a stop, right? So my F net, everything's breaking here. So just 1 second. Oh, that was faster than I thought it would be. My F, the reason I want to find my F net, because I have to find the acceleration. Because to find my, I have to find the acceleration eventually. To find my I have to find my F net. My F net is equal to mass times acceleration. So if I can find my acceleration, I can find my FF, and I can use that over on the other side there. So I'm going to have to find my acceleration here. So let's see, what is our acceleration? Question mark here. We got D, it travels 5, it comes to a stop. It's got an initial velocity of 1.4 meters per second. What formula would I use here? Oh, it's that VF squared formula. The one we use it quite often, don't we? VI squared plus 2AD. We're going to rearrange this. I'm going to minus over the VF there, or the VI squared, minus VI squared over. Then I'm going to divide both sides by 2 and D at the same time. And we're going to get A is equal to VF squared, so 0 minus 1.4 squared divided by 2 times 0.25. So we get a negative 3.2 or 92 meters per second squared. Now the reason it's negative because it's slowing it down. I'm not too concerned about that. All right. The reason I'm not too concerned about that is because all this formula over here involves just a bunch of absolute values. Okay, so I got my Fn already. Perfect. We need to use this to help me find the FF, and the FF is equal to mass times acceleration, because that's equal to my F net. So I take this times by my mass. So we have 5.88. And again, I'm just worried about my absolute value here. 5.88 newtons. And then I can go back. Now I take these two things here. Take this one, that goes over here. I take this one, that goes up there. And I can find my mu, dividing these two numbers. 0.399, 2 sig digs here, so 40. And it's unitless, right? Mass divided by mass, or sorry, newtons divided by newtons. That cancels out. We got two objects here. They have a force between them. What's the distance between the centers? Okay, so this is just a nice little formula here. We got force is equal to gmm over r squared. Remember, two massed objects are going to be attracted to each other through this formula. And I can determine the distance between them by rearranging the equation. So timesing the r squared up to both sides, and then dividing fg down to the other side, right? All right, and then, oh yeah, and the last thing to do, take the square root of both sides. This is an easy question. What does it end up being? So remember, g is 6.67 times 10 to the negative 11 times by my mass times the other mass divided by the fg. And the last thing I'm going to do is take that square root, right? So it looks like I'm only about 2 meters apart from this guy. Really small force. 3 sig digs? 0.6 meters. There you go. Because it's 5, 5, and the 5 rounds up. That's not too bad. Determine the magnitude and the distance traveled horizontally by bullet to the bullet. Oh, okay. Fired horizontally from bullet. That's 1.5 meters on the ground. So it's like a shot from the hip or something. How long does it take to fall to the ground? Ignoring the curvature of the earth and assume the ground is pretty flat. I think we can do this. Now the reason this curvature is probably not too important, the distance is probably not going to be that far. As it gets further, you might start noticing the ground is falling from you. So here we got a bullet, shoots off, it's going to fall to the ground, hit the ground, and we're here, it's going to fall down 1.5 meters. We're trying to find horizontally what is this distance here, right? So because of this projectile motion part, we've got this kind of T-chart, right? We have our vertical section where our acceleration down is negative 9.81 meters per second squared. It's traveling down negative 1.5 meters. It has an initial vertical velocity of 0 because it's horizontal. Right? That's important. And we want to find something. Time or VF. Most likely going to be find time, right? Because what we're going to do is we're going to use that time over here. If I can find out what that time is, I can use it over this side. Because in the horizontal direction, there is no acceleration. A is equal to 0. I'm assuming that there's very little resistance on the bullet horizontally. If there's very little resistance, nothing's going to be pushing on it to slow it down, right? So my A is going to be equal to 0. And if it's shot horizontally, that's going to be my my initial velocity in the horizontal direction, but it never changes because there's no acceleration. So it's like my initial and my final at the same time. It's my average velocity, so it's just going to stay about that. If I want to find D, I have to go V times T, because remember we're using this formula. V is equal to D over T. I multiply both sides by T, and we get V is equal to D times T, or V times T, sorry. D is equal to V times T. Okay, so we need to find the time. So we come to this side over here, we say, okay, time, what do we want to use to find time? There's no VF. Okay, so this is a good formula. We can use the VIT plus 1/2 AT squared. And you're like, oh man, there's two T's again. We got this thing where we got T squared and a T, and then what do we do? Oh, but then we quickly calm down. We say, oh yeah, that's right. VI is equal to 0, right? So delta D 1/2 AT squared We can cancel that first term because vi is equal to 0. Now it's much easier to solve for t now. So I times by 2 on both sides. Get rid of the half. Okay? We divide by a on both sides to get rid of the a. We take the square root on both sides to get rid of the square. And we have all the information there, so we got 2 times the 1.5, negative 1.5 if you want to include the negatives, divided by negative 9.81. Okay. And then we just have to take the square root of that answer, and we get 0.553 seconds. So now what we can do, we take that, go up here, use that in that time. 4.0 meters, 450 meters per second times 0.553 seconds. It's going to travel 249 meters. Looks like it's displacement. But it's not displacement, we're just looking for the distance covered. So 249. There we go. I think that's it. Okay, happy studying. I'll see you all tomorrow for the test, bright and early, 9 o'clock. Show up a little bit earlier. Get a good night's sleep. Okay, bye.